Richard Feynman. He said that it doesn't matter how beautiful your theory is, how beautiful your mathematics of your theory is, the experiment will decide that which is true, what is the right thing.
When I woke up this morning, it was a bit late, but I didn't care, so I just went ahead and prepared myself. Then I looked at the mirror, my eye was good, so I said to myself, I'm ready to the world. I'm ready to the world.
There are many predictions by theoretical physicists, and also there can be phenomena which is not predicted at all. Also, theories can be contradictory to each other. Suppose some theory may say this specific particle should exist at this mass, and some other theory may say this particle should not be there. So in those cases, it is the experiment who should decide that who is right, which theory is right. And experiments give us the true information and help us to shape our understandings about our universe. Large Hadron Collider, which is the largest machine of the world, it has a gigantic ring which has 27-kilometer long circular tunnel where protons which travel at a very high speed. The speed is 99.999999, I mean 0.69% a speed of light. At a huge speed, the protons that pass through the circular tunnel and they collide. And the LHC ring, we have 4 different points where we have the 4 major experiments, 4 major detectors are placed. So at those points, the 2 opposite beams actually collide, and we record lots of events take place there. New particles come out from that collision, and from that collision, to measure those particles, we have placed 4 different major detectors. So one of the detectors is ATLAS experiment. ATLAS is the largest volume particle detector. It is 46 meter long, 25 meter diameter, and 7,000 ton its weight is. It is a general purpose detector. I mean, we can search anything with the ATLAS experiment, unlike the other 2 experiments, LHCb and ALICE. So those 2 experiments are dedicated for some particular reasons. They have some particular physics goals, and they want to just concentrate on those physics problems. Those are also equally important. But at ATLAS or CMS, in these 2 experiments, general purpose experiments, we search for, we also search for those things. We also, some few people from our collaboration, they work on those things as well. But we can search for anything. We search for dark matter, we search for supersymmetry, we search for new particles which are predicted by our theorists, that they predict that this particle should be there to solve this mystery, or this particle should interact in this way. We do all kinds of studies with particle collider, whatever is possible with the collider physics. Actually, there are different groups. Suppose I am working with some of the groups. Some people are developing some electronics which is needed in the core of the detector. Some of our colleagues, they're developing some mathematical or computational models actually. So for example, you may have heard about the machine learning and artificial intelligence. These are very emerging actually fields or emerging techniques. So at CERN also, in the ATLAS group also, there are many people who dedicatedly develop those algorithms, those techniques, the technologies, and see that how we can use those technologies into our experiments. In the ATLAS experiment, we have different layers of sub-detectors. Surrounding the beam pipe, we have inner tracker, or we say ITK. So in a tracker, we track actually, so the charged particles, which pass through that inner tracker. So we can form the tracks that, okay, this is the path the particle has passed. So how much the particle has bent. All those things we can calculate from there. And after passing the tracks, we can reconstruct the tracks. And after the inner tracker, then the next layer is calorimeter. The calorimeter is a part where we can measure the energy. So some of the particles which pass through the inner tracker, and they end up at calorimeter. So different particles have different, they travel different distance actually. Some particles end up very, very soon. Some particles travel a lot. Suppose some particles end up in electromagnetic calorimeter. Some particles traveled electronic past it, and then it ended hadronic calorimeter. Then we have muons, which doesn't stop at all. They just pass through the detector. But we have the muon spectrometers at the end of the detector, where we can measure the momentum, which momentum and and some of the other properties that how the muon has passed. So from that, those information, after collecting those information, we gather that how the muon has passed, what has been its energy, or many other different properties. So these different layers have different actually functions. As I mentioned, that in a tracker, we track, we measure, we reconstruct the tracks, and the calorimeter, for the electromagnetic calorimeter, we measure the energy of photons and electrons, and then we have hadronic calorimeters, some hadrons like protons, they actually end up there. So it's a very complex detector we have, and a huge detector we have, and lots of electronics are needed, lots of new technologies are needed. Okay, sometimes superconducting wires, and we need sometimes very cool. We need liquid helium, sometimes liquid argon. So we need very advanced magnets. So it's a very, very complex detector, and it's a very complex machine to run. And that's why we need actually so many people to run this huge, gigantic machine. Some people are developing some computational programs, how to access the data, or suppose at first we got the hits in a tracker, how the electronics will tell us that, okay, what has happened there. Because we cannot see, right? We see from the electronics, we get signals from the electronics. We have some photomultiplier tubes somewhere where, I mean, whenever there are sometimes, okay, there are some of the technologies where whenever charged particle pass, there's a scintillation, there's some flash of light. So from that flash of light, we can say, okay, some particle has passed. Exactly where the particle has passed can get some information from that module. So it's a very complicated our experiment is, and that's how our physicists are divided into different groups. For each layer of the detector, there are dedicated groups, or they're dedicated research. So day and night, they're just thinking and developing things. They're maintaining how to, I mean, develop it or how to maintain it. Particles are passing through inner tracker, calorimeter, muon spectrometer, right? This is how it is coming. And there are lots of subdetectors. There are lots of electronics. So we need to make sure that everything from starting from the collision point, beam point, up to the end, we have everything perfect. It's a huge task. The next comes is the data collection, how the data will be collected, whether all the data will be collected or we want to get only the interesting data. Interesting data means which are useful, okay? Or I mean, how to process the useful data. There are different parameters, the way we reconstruct. And whenever we reconstruct, okay, we have got this particle has passed through the detector. And this was its drag, this was its transverse momentum, this was its energy, and eta, phi, lots of different parameters. It was its mass. Okay, so using all those informations, we reconstruct each particle, and there are each identification techniques. Different groups actually work on the different identification techniques of different particles. Using the data, we look for some distinct signatures. Suppose if I want to identify charged Higgs boson, or any particle, the W prime boson, and we say, okay, this is the decay product. This particle will be decaying to these smaller particles, and that particle will be decaying to that smaller particle, another particle. So we need to understand that what are the final state of particles, and then we will use the identification techniques of all those different particles, and we will combine all the techniques together, and we will be, all the underlying dynamics. We will consider that how it has, okay, sometimes it may be some jet, and inside the jet there was some smaller jet. So we combine all of them, and then we look for, there is a standard model of particle physics, which predicts that, which does some prediction, and this is a very successful theory. It explains many of the things, many of the dynamics of the particle physics world. But it has also many disadvantages as well. Many of the different things are there which standard model cannot describe. But many other theorists we have, they have some new predictions, they have new models, there are new theories, and according to those predictions, we try to search the new particles, and we, as I mentioned, we just collect, we combine all the different techniques from the data collected, and then we reconstruct them, and we compare the standard model, and standard model prediction, and whenever we say, if we find some significant deviation from the standard model prediction, then okay, so we'll say, okay, we have found something new. We do very generic searches. Generic searches means We are just looking for some range, and if we find some deviation from the standard model, that may not be motivated by some particular theory. We do searches for model-specific and prediction-specific searches or prediction-specific studies, but at the same time, we do some generic studies as well. At the same time, we do very precise measurements, many measurements, the measurements of some parameters or some mass of some particle. I mean, very high precision actually. And there is actually also interesting fact that if we find the standard model actually also predict the value, and if someone gets the precise, very high precision, at very high precision, if they get some different value, even if it's a very minor difference, very small difference, that can be also a signature of something new. Actually, many people focus on precision measurements. They measure it with very high precision, and they look there whether they get some deviation from the standard model prediction at their prediction. So we do measurements, we do searches, okay, and we are just trying as a whole collaboration, Atlas experiments. We have thousands of people, thousands of physicists across the world. Together, we are trying to understand the universe better. We are trying to solve some of the mysteries of the universe.
Is there some particular specialty you do on the Atlas experiment?
I work on different things. Currently, I am searching for two new particles, just like the Higgs boson was proposed as a new particle some time ago, many years ago, and people were searching for Higgs boson over 50 years, and finally they found in 2012 at CERN in our Atlas and CMS experiments. Similarly, there are many different particles, new particles are there. I'm searching for two different particles, new particles proposed by theorists. One of them is a W prime boson. In the standard model of particle physics, we have W boson and Z boson. They are very important particles for weak interaction. So similarly, we have W prime boson, but it has some new properties, and many different theories actually predict that there should be W prime boson and Z prime boson, just like W and Z boson. So I'm searching for W prime boson. That's a new particle. And also I have been searching for another new particle. It's called charged Higgs boson for Atlas experiment. So charged Higgs boson is just like the Higgs boson was discovered in 2012. And it was a groundbreaking discovery. But since we found the Higgs boson and it decays in certain ways, the question arises that is it the only Higgs, or there should be more Higgses, or where there should be different kinds of Higgses? There are many theories, actually, very interesting theories, which predict that there should be more Higgses. There's a popular 2HDM model, and also there are many other models which predict there should be charged Higgs, there should be doubly charged Higgs, there are different properties. CP even, CP odd, different kinds of properties are there, and they predict that there is a Higgs family, and this current Higgs, which we have discovered in 2012, is only one of the member of that family. So if we find, more Higgses, our understanding of our nature, of our universe, how everything works, or whether how it can give masses to more particles, a new area of our understanding will open. I worked a little bit for the upgrades of high luminosity LHC. High luminosity LHC will be the upgraded version of the current LHC, where we have way more luminosity. Luminosity means, very naively I can explain that we have more particles which will be colliding, and way more collision will be taking place at that tunnel, detectors. So for that, we need many upgraded technologies, because the plan which we have for high luminosity LHC and the current infrastructure which we have, some of the techniques needs to be upgraded. So I worked a little bit for the upgrade studies. One of the upgrade studies for this high luminosity LHC, which will be coming up upgraded in around 2025 or 2026, around that time. Specifically at Atlas, as I say, that we have general purpose detectors, and we do all kinds of different kinds of searches, and we deal with almost all kinds of particles which we have in the standard model, and one of the particles is b-quark. So b-quark, that's a very important particle. How do we find a new particle? Whenever we find suppose a new particle, and there are some decay modes. If there is a heavy particle, the decay is into smaller particles. So if we want to detect some higher new particle with higher mass, we need to find out the tracks that what are the different decay products they decayed into. We need to have the technology to identify those particles which are in the final state. If we can find those final states, and then we can connect the dots, and we can say, okay, these particles came from this new particle, or all these smaller particles, they are originated from this heavy mass particle. Okay, so that's how it works. So, for example, Higgs boson, which was a groundbreaking discovery. So Higgs actually decays most of the time into pair of b-quarks, and B and anti-B. So you can understand how important the identification techniques of b-quark is in the LHC or in the ATLAS program. So I personally work on developing some techniques for the b-quarks. So we develop some new technologies, how we can find out, how we can identify the b-quark at our ATLAS experiment more effectively. So for that, it is not only for Higgs, but in many different actually physics, in many different particles, we have b-quarks in the final state. In supersymmetry, in the search of supersymmetry, in the search for dark matter, and many other kind of searches, we have b-quarks in the final state. So it is very important to develop better identification techniques for the b-quarks.
And how did you involve into ATLAS experiment?
So ATLAS experiment is, as I mentioned, is a huge collaboration. So it's a huge collaboration. We have around 180 plus institutes actually across the world. They're part of ATLAS. Many different universities participate in ATLAS. So I wanted to do my PhD or my research in particle physics. So I searched that what are the universities that those are participating in the LHC program, or they're working with CERN or working actively in particle physics. So since my university, my current university, that is actively participating in ATLAS experiment, I joined that research group, and that's how I am working with that ATLAS experiment. But before coming here, as I mentioned, before starting my PhD, I worked at CERN for some time as an intern. That was just after my MSc. I got selected at CERN, the program by CERN. So I went to CERN and I worked a few months. And later on, when I came to the United States, then I joined the research group of ATLAS.
And is it that you were also in Fermilab?
Yes, actually. So I got a fellowship 3 years ago. And due to the fellowship, I went to Argonne National Lab. So that's a national laboratory of United States. And at Argonne, I go, due to the fellowship, I worked there for 1.5 years. And our experimental apparatus was at Fermilab. So Argonne National Lab and Fermi National Lab, or Fermilab, they are very close actually. So though I used to work for Argonne, but I had to go to Fermilab to perform my experiments. So half of the day I used to at Argonne National Lab, half of the day I used to be at Fermi National Lab. Two national labs, I had to drive every day.
What do you like most about your job?
I like the fact that I am trying to understand how our universe works. So our work is very universal. Though, I mean, suppose I am sitting in a small office, or maybe in the our theory friends as well, when they do some small calculation. This is the beauty of physics, right? You can do the way logically you can explain things. While sitting here, we explain that what is happening at the core of the sun, right? Or what kind of nuclear synthesis is happening in some distant star, or by just looking at some spectroscopy or the light which is coming from the different stars, you can say, okay, this metal, or these components are there in this particular star. So this is something I find very amazing, that the way you extrapolate, not only extrapolate, I say the way you logically conclude, using some simple laws, if those simple laws actually are valid everywhere, okay, so you can predict things. So what I particularly like is, I get very happy to think that I'm trying to I'm working on some of the problems which are, if those things are solved, our understanding about our universe, or about how the universe works, very underlying mechanics or dynamics, you can say, we will get some new insight about it. So that's what I feel very happy about it when I do research, or when I study, and when I go to CERN. And CERN is actually a really amazing place, and it was my dream actually to go to CERN someday, and to see those, not only CERN but also the other labs like Fermilab. Fermilab was the biggest lab actually before CERN. Right now you can say the second biggest lab after CERN. So at Fermilab, Argonne National Lab, and then Stanford National Lab, Los Alamos, and all these things, actually, it was my dream to visit those labs. But so far, I have been lucky, very lucky. I have visited all those places. I have all those labs. When I was a college student, it was my dream to see CERN someday in my open eyes. And right now, it has been only 5 years I have been working for CERN, or with in association with CERN. And so I feel happy about it.
Thank you very much for your time. It was a pleasure to meet you. Oh, I'm so proud of you. Yeah, so it could be great. It's my dream to look at to see it.
143 meters. So underground, and it's walking, make the different cartoons, and
So the beauty of physics is going to be exciting, you know.
it's a huge experiment, gigantic experiment.
Amazing. It is amazing.
Something
Oh.